Good morning to all. So today's class, I'm going to discuss about the relation between IDS versus VDS. Right? How we are going to implement the current that between drain to source. What are the major parameters we are going to discuss here, and how it is going to be derived based on this concept. So now we want to see now. Okay. So drain to source current, IDS versus VDS relationship. Let us hear what we discussed now. That will be considered here. These are point. First point here it is the entire concept of the MOS transistor. The entire concept of the MOS transistor evaluate from the use of voltage on the gate. That voltage induces a charge in the channel between source and drain, which may cause it to move charge carriers from source to drain under the influence of electric field. So the movement of charge carriers source to drain by the applied voltage, that is VDS, between drain and source, right? Once again, the entire concept of MOS transistor evaluates. The entire concept of MOS transistors evaluates from the use of voltage. The voltage nothing but gate voltage. So due to this gate voltage, the charge is induced. The charge is induced in the channel between source and drain. So that due to the channel, that charge is nothing but which may cause to move so charge carriers from source to drain under the influence of electric field created. So those moment of charge carriers are moved from the moment of charge carriers is nothing but the movement is occurred in between those charge carriers from source to drain due to the applied voltage. That voltage nothing but VDS. Okay, so due to this voltage, the charge carriers movement is occurred between the drain and source. Right. Next, second point. Since the charge induced is dependent, on the gate to source voltage. That is nothing but VGS. As I told you now, here the charge is induced depending on the gate voltage with respect to source or substrate. Then IDS is dependent. IDS is nothing means the IDS is dependent on both VGS and VDS. How it is dependent on both VGS and VDS? So by this VGS voltage, the charge is induced in the channel, means the channel is established in between source and drain. Okay, if the channel is available, then the charge carriers are ready to move from source to drain. If you are applying any external force at drain, that force is nothing but, here we are saying it is nothing but VDS. So due to this force, the channel is available due to this VGS. The electrons, whatever it may be, the charge carriers are movement will be occur in between source to drain. Then we are expecting that is current IDS. So due to that, IDS is dependent on both VGS and VDS. Right. Next point. Consider a structure here in figure in which electrons will flow source to drain. Electrons will flow source to drain. Means here in this figure we consider here it is a NMOS transistor. NMOS transistor. Okay, this is a structure. This is the top side view of three dimension of NMOS transistor structures. Okay, let us observe here. This is the source region, and this is the drain region. This is the gate region, right? And this is the substrate here. This is the substrate. Okay. So these are the N-type diffuse region, means the substrate is P-type, right? Let us see here. The length of the channel is L, and the width of the channel is nothing but W, and the insulating layer here, insulating layer nothing but it is a, the thickness of the insulating layer it is nothing but, dioxide layer nothing but D. Okay. Now, so when we are applying a gate voltage, due to that voltage, the channel is established in between source and drain, in between source and drain. Then the charge carriers, whatever the charge carriers are at source, they are ready to move from source to drain to this direction. If you are applying any voltage, that is drain voltage, that is nothing but VDS. Okay, due to this voltage, the electrons are moving from source to drain. Then we are expecting there is a current, that current nothing but IDS, that is opposite direction. The current is going to be electron movement opposite direction, drain to source, nothing but it is IDS, right? So this is the equation here, IDS equal to minus IST equal to, okay, charge induced in channel, that is represented with QC by electron transit time. Electron transit time, that is tau st, tau. It is denoted with the tau. So firstly, we want to discuss the denominator part here. Okay, that is transition time. Tau sd is tau. Tau s transition time means the electrons are moving from one position to, there is a movement of charge carrier from changing the movement of charge carriers, changing the position of the charge carriers from one position to another position with a certain amount of speed, means that nothing but transition time. So firstly, we can find that transition time here. That is nothing but here the movement of charge carrier is occur along the channel with a velocity, with a certain amount of velocity. That's why here transition time tau sd equal to length of the channel L by velocity of the charge carrier, that is denoted as V. Length of the channel L by velocity V. This is the equation number 1, sorry, the equation number 2, and this is the equation number 1. Okay, keep remember these two equations. Next, but velocity is equal to, velocity means if there is a field, then the charge carriers are moving from one position to another position with a certain amount of energy. They will be gained to move from one position to another position. That is nothing but maximum speed attained by the charge carrier from one position to another position. Nothing but it is mu. The complete ratio is nothing but here product is given nothing but is a velocity of the charge carrier, V equal to mu into EDS, where mu is called as mobility, electron mobility or hole mobility on surface, right? Next, EDS nothing but electric field that will be induces in the channel in between source and drain due to the gate voltage. Of course, it is gate voltage, right? EDS equal to electric field, that is drain to source. So now we want to discuss this. We want to find this EDS. EDS equal to VDS by L. So how it will be occur? Means applied voltage in between drain to source along the channel. There is a change in electric field, right? Means the voltage drop across the channel, the maximum the voltage drop along the channel. Then there is a change will be occurs in the channel due to the IR drop. Okay? So EDS equal to VDS by L. So substitute this EDS value in equation V and then this value in equation 2. So substitute the electric field value in velocity V equal to mu into VDS by L, right? So this value in EDS. So V equal to mu into VDS by L. So this is the formation. V equal to mu into VDS by L. But we know that the transition time equal to what is this? Here L by V, length of the channel L by velocity V, right? That's why I'm saying here keep these equations, right? Therefore, the transition time is tau sd equal to, substitute this value in equation here, equation 2. So L by mu VDS by L. L by mu VDS by L. So let us see here. Tau SD equal to L by V. This is tau SD, right? So we know that V nothing but this value. So substitute the value in equation here, then automatically we are getting here L by mu VDS by L, right? So then L square by mu VDS, right? This is the transition equation number 3. Okay, next. So here the mu is nothing but mobility of the charge carriers. The typical value of mu at room temperature, or that is for electron 650 centimeter per volt centimeter square per volt second on surface, and for holes 240 centimeter square per volt second. This is the values for mu n and mu p, right? Next case. Next. Here we can observe the device is in 2 modes. Generally it is in 3 modes. One is cutoff mode, and second one is non-saturated mode, and third one is saturated mode. Non-saturated means it is on condition. It is in active condition. Somewhat means it is also called as a resistive region. And saturation means completely on means it is in deliver the response. That is saturated. Okay. Here VDS in non-saturation region. Let us observe discuss these points here. The charge induced in channel. Due to gate voltage. Due to the gate voltage. The difference between the gate and the channel, that is VGS. The difference between gate and channel, right? Assuming the substrate to source, right? Next, the second point is note that the voltage along the channel varying linearly, right? The voltage is varying along the channel with the distance x from the source to drain due to the IR drop in the channel. Okay, as I told you in previous classes, there is a enhancement mode transition action. By varying the VDS, the channel length is also varying. That is the distance in between source to drain x is varying from source to drain due to the IR drop along the channel. Okay, that will be linearly. The channel is various linearly. Suppose let us see here. This is a source region and this is the drain region. Here we are applying the VDS. Then the channel is linearly varying. Linearly it is varying like this. Linear varying, right? So assuming that the device is not in saturated, then the average value. The device is not in saturated mode. It's not completely deliver the response. So the channel is like this linear mode. So here we are applying voltage. The average voltage along the channel nothing but VDS by 2. VDS by 2. Okay. So device in non-saturated region, then the average value of drain voltage nothing but VDS by 2. Okay. Furthermore, the effective gate voltage VG equal to VGS minus VT. So what is meant by VT here? VT is nothing but threshold voltage. Threshold voltage. It is the minimum voltage. If your applied voltage exceeding that level, then the device is going to changing its properties, conducting properties, right? So here applied gate voltage, that is equal to VGS minus VT, that the device is in non-saturated region. So where VT is the threshold voltage needed to invert the charge under the gate and establish the channel due to this voltage. The channel is established in the channel. The channel is established in between drain to source due to the gate voltage. Right? This is the concept here in non-saturated mode. It is in simply like it is in active mode, means it is in resistive mode. So So here the channel is induced due to gate voltage in between source and drain, and also the channel is varying along the distance by applying the drain voltage. So finally we are getting we want to calculate the average drain voltage along the channel, that is equal to VDS by 2, right? Next, note that here the charge per unit area, charge, that is nothing but QC, charge per unit area. So area is nothing but width of the channel into length of the channel. Okay, so area is nothing but length into width, length into width. Okay, so here the charge per unit area is that equal to EZ, right? Electric field due to gate, insulation, epsilon insulation and epsilon permittivity, right? So that charge is equal to QC equal to EZ in epsilon insulation, epsilon naught, and area of the channel, area of the channel. Okay, next, where EZ equal to average electric field gate to channel, average electric field. Similarly, epsilon insulation, relative permittivity of insulation between gate and channel, and epsilon naught is permittivity of free space. And here the epsilon values and epsilon insulation values for silicon dioxide layer. So let us remember these values, right? Okay. Here, up to this part, the denominator part is over. Now we are going to be discuss the now we want to calculate the numerator part. For that, we need to calculate QC, the charge induced in the channel per unit area. That is nothing but this way, right? Now you want to calculate the gate electric field at a gate, average electric field. That is equal to VGS minus VT. That is nothing but applied voltage, and VDS by 2. It is the average voltage, and D is the thickness of the dioxide layer. The difference between applied voltage and average drain voltage with respect to ratio with respect to thickness of the dioxide layer, nothing but average electric field. So where D nothing but oxide thickness. Therefore, the charge per unit area, complete charge, here we want to calculate complete charge here, QC, nothing but epsilon insulation, epsilon naught, WL by D into VGS minus VT in minus VDS by 2. So this value you can substitute in this equation, right? This value instead of EZ, right? So EZ nothing but VGS minus VT minus VDS by 2 whole divided by T. This value substitute in equation here, charge per unit area. So then QC equal to epsilon insulation, epsilon naught WL into VGS minus VT minus VDS by 2 in like this. This is the equation number 4. Okay, keep remember this equation. Now, the transition time is over. The charge induced in the channel is over. Now combining equation 4 and equation 3, that is transition time, and then substitute in equation number 1, right? So then IDS equal to epsilon insulation epsilon naught mu W by L into D. Sorry, epsilon insulation epsilon naught mu by D into W by L, width by channel length, into VGS minus VT minus VDS by 2 into VDS, or like this. So IDS equal to K into W by L. K is nothing but this value. We can represent for simplification. For simplification point of view, we can write epsilon insulation epsilon naught mu by D is nothing but K. That is equal to VG, that is product of K into W by L into VGS minus VT minus VDS whole square by 2. So how VDS is nothing, VDS square nothing but here this VDS is multiplied inside. So VGS minus VT into VDS minus V square DS by 2, right? This is the current equation now. So in non-saturated or resistive region, as I told you, the device in non-saturated or it is in resistive region, VDS is less than VGS minus VT. VDS is less than VGS minus VT. And for the simplification, we can write K equal to epsilon insulation epsilon naught into mu by D. And the factor W by L is of course contributed by the geometry, and it is common in practice for beta equal to K into W by L. So for this here, K into W by L for the simplification geometric point of view, geometric parameter, that is Ids equal to K into W by L. We can write here that is beta. So that Ids equal to beta into Vgs minus Vt into Vds minus V square ds by 2. This is the another form of equation 5. This is the general equation. Another form of equation 5, that is 5.1. So means it is alternative form of our current equation. It is equation from the 5. Now, another point here, that gate per channel capacitance also available there, because of there is a parallel plates. Okay, so here this is the region here, and this is we are going to be here. This is the polysilicon layer, nothing but it is gate layer. Here oxide, this plate nothing but here it will act as a capacitive plates. These two plates are nothing but parallel plates. This is source and this is drain. This plate is nothing but parallel plates. Okay, that will be also calculating here. Gate capacitance, gate per channel capacitance or gate per channel capacitance. So here CG, nothing but gate capacitance. That is the ratio with respect to epsilon insulation, epsilon naught, and length of the channel by thickness of the dioxide. Okay, so for the simplification from from this value, this equation K and CG, based on these two parameters, this parameter and this parameter, for the simplification we can write K equal to Cg into mu by W. How it can write here? Let us see here. So here let us see here K equal to epsilon insulation epsilon naught mu by D, right? Here Cg equal to epsilon insulation epsilon naught by D into WL. Okay, so here it is epsilon insulation, so epsilon insulation epsilon naught by D, that is equal to K by mu. Let us see here, epsilon insulation and epsilon naught by D equal to K by mu, right? Epsilon insulation and epsilon naught. Instead of this term, we can write K by mu, right? K by mu in this formation. Okay, so in this place, you can write K by mu. Cg equal to, okay, Cg equal to K by mu into WL, right? So then K equal to Cg into mu by WL. This is the formation, right? K equal to Cg into mu by WL. Okay, so that Ids equal to Cg into mu by L square. Okay, so here K equal to Cg into mu by WL, but generally here let us see here from this equation 5, from equation 5 here, Ids equal to K into W by L. Okay, now you can write here Cg equal to K equal Cg into mu by WL. You can substitute this value in equation 5, then we can get Ids equal to Cg into mu by L square. W is cancelled, L into L square of Vgs minus Vt into Vds minus V square ds by 2. This is the another form of equation number 5, or alternative form of equation 5. Okay, next. Sometimes it is convenient to use gate capacitance for unit area, nothing but C naught. They represent with the C naught, and which is often denoted as C naught X also. Because of why it is X, because of it is the distance. If the distance going to be increases, the channel will be affected from source to drain. So rather than CG in this and other expression, noting that here CG equal to C naught into W. CG equal to C naught into W. Substitute this value in equation number 5.2. So IDS equal to C naught mu W by L VGS minus VT into VDS minus V square DS by 2. This is the equation 5.3. So these are the 5.1, 5.2, 5.3 are the alternative equations of equation number 5. That is current equation. Why we are going to do like this? Based on a given requirement, we can use out of these three equations. Okay, right? Next, in saturation condition, in saturation position, saturation means VDS is equal to VGS minus VT. In previous case, VDS is less than VGS minus VT, right? So here VDS equal VGS minus VT. Since at this point IR drop in the channel equals effective gate to channel voltage at the drain, we may assume that the current remain fairly constant, right? Because of there is no channel in between source and drain. So that is, let us see here like this. This is the source region, this is the drain region, so this is the channel like this. So this region nothing but, as I told you in previous class, this region nothing but pinch off region. The current is constant, right? Okay. Thus IDS equal to K into W by L. So here in previous case, instead of VGS minus VT, we can write VDS because of the device is in saturation condition. So let us see here. That is in equation number 5. Here we can take the equation number 5. So this is the equation 5 here. IDS equal to K into W by L of VGS minus VT into VDS minus V square DS by 2. This is equation number 5. But it is in non-saturation. But we need to calculate saturation mode. At saturation mode, VDS equal to VGS minus VT. So you can substitute instead of VGS minus VT, that is VDS. Okay, VDS. Instead of this value, you can substitute VDS, right? So here, so then automatically VDS into VDS, V square DS minus V square DS by 2. Let us go through that point here. So this is the point here, right? So IDS equal to K into W by L, VGS minus VT whole square. Okay. Generally, after getting this value here, V square DS. Okay, V square DS minus V square DS by 2. So you need to LCM here. So V square DS by 1 and V square DS by 2. The LCM is 2 here. So 2 into, so V square DS minus V square DS, right? 2 V square minus V square nothing but V square DS by 2. This is the final point here. So out of this completion point, okay. So now IDS equal K into W by L into V square DS by 2. Again, you can substitute V square DS instead of V square DS, that is VGS minus VT, right? Let us see here. This is the point. So from that equation, you get IDS equal to, in what we have to simplify in previous slide. So here K into W by L, that is V square DS by 2, right? But here VDS nothing but VGS minus VT. Again, you can substitute VGS minus VT instead of VDS. Then this is the equation. IDS equal to K into W by L, VGS minus VT whole square by 2. So for this equation, okay, equation number 6, it is in saturation mode. And the similar way, there is another form of this is equation 6 in saturation mode. So we may write, that is, we may write K into W by L, nothing but already I told you beta is equal to K into W by L. So here nothing but beta, the 2 is here. So beta by 2 into Vgs minus Vt whole square. Ideas equal beta by 2 Vgs minus Vt whole square. That is equation number 6.1. This is the alternative form of equation 6. Next, or ideas equal Cz into mu by 2L. As previously calculated there in non-saturation mode, ideas equal in terms of gate capacitance value. In terms of gate capacitance, right? Ideas equal Cz into mu by 2L square Vgs minus Vt whole square. That is equation number 6. We may write also in terms of Cg in terms of C0. Okay, gate capacitance. So ideas equal to C0 into mu into W by 2L, that is Vgs minus Vt whole square. This is equation number 3. So it's equation number 6.1, 6.2, 6.3 are the alternative form of equation 6. According to our requirement, according to the given parameter, we can use instead of out of these 4 equations in saturation mode. Similarly, in non-saturation mode, there are also we are getting 4 equations based on requirement. We need to calculate some values. So we need to calculate the values for in saturation mode. Out of those 4, we can use according to the given parameters. Right. Right. Next. So this the expression derived for IDS hold for both enhancement mode and depletion mode. But it should be noted that threshold voltage for NMOS depletion mode, that is denoted as VTD, is negative, right? Whereas in enhancement mode it is positive, whereas in depletion mode it is negative. Okay. Now we want to show here. I am showing. I am going to discuss along, that is characteristics of NMOS transistor and depletion mode transistor. NMOS depletion mode and enhancement mode transistor. That thing also going to be showing here. That is the typical characteristic NMOS transistor, that is showing figure here. See, this is the MOS transistor characteristics. This is in it is in depletion mode and it is going to be enhancement mode. So clearly you can observe here. So this thick line, it is showing here. The arrow mark is showing here. The thick line nothing but it is the thick line, it is nothing but a depletion mode. Here there is no thick line, nothing but it is in enhancement mode, right? Already know that you know these characteristics, VDS versus IDS, and here VDS versus IDS. Like that, it is a FET characteristics, right? So it is in depletion mode. Here VDS going to be increases, that is 0.5 VDD and VDD along the x-axis we are going to apply. So based on this, we are expecting there is a current where different values of VGS. It is in depletion mode because of if it is in depletion mode means the channel is already the channel is available in between source and drain. So we need to be remove the channel. We need to be remove the channel. So then we can apply the voltage, that is negative voltage at gate, right? That is for that VGS equal to minus 0.3 VDD and VGS equal minus 0.11 VDD. And then VGS equals 0, and then like this. Based on different values of this, the current will be going like this. And similarly, here it is enhancement mode. We need to establish the channel. We need to create the channel at different values of VGS. It is in positive value because of there is no channel. We need to establish. Then we need to give the positive values. That is positive gate value. So for that, we just equal to 0.0 VDD and 0.4 VDD and 0.5 VDD, right? 0.28 like that. Based on the different values of input, that is drain voltage, we are expecting the current in different regions. Okay. So this is the complete procedure of for the derivation of that is the relationship between IDS versus VDS, drain to source current and drain to source voltage. Drain to source current dependent on both gate to source voltage and drain to source voltage. How it is going to be implemented. So what are the major parameters we are here we are going to be we are discussed for the implementation of, that is IDS versus VDS relationship. All those things are going to be uh, based on this concept. We need to calculate if any problematic questions are given. So based on that given parameters and requirement, we need to use out of these six current equations according to the given data. Thank you.